Good day, ladies and gentlemen. Today, we're going to talk about the Ericcson cycle. The Ericcson cycle is a thermodynamic cycle proposed in the 19th century, and it represents as an alternative to the more well-known Carnot and Stirling cycles. The Ericcson cycle is named after John Ericcson, who was born in 1803 to 1889, a Swedish-American inventor and mechanical engineer. Ericcson developed this cycle in the late 1830s and 1840s as part of his work on external combustion engines, particularly in his quest to improve steam engine efficiency. During the early 19th century, inventors and engineers were exploring safer and more efficient alternatives to steam engines, which were prone to explosions due to high-pressure boilers. John Ericcson, like Robert Stirling, pursued the idea of an external combustion engine that avoided these dangers. Ericcson introduced a hot air engine using what we now describe as the Ericcson cycle, which used regeneration, heat exchange to improve thermal efficiency. Ericcson built several engines based on this cycle. His 1833 designs involved two isothermal processes, which is expansion and compression, and two constant pressure processes, which is heat addition and heat rejection. Unlike the Stirling engine, which uses constant volume processes, the Ericcson engine uses constant pressure regeneration, making it thermodynamically distinct. In 1851, he built a large hot air engine to power a ship called the Ericcson, aiming to use this engine for maritime propulsion. While the ship had limited success, it was a major step towards advancing heat engine design. The Ericcson cycle consists of isothermal expansion, which is heat absorption, constant pressure regeneration, isothermal compression, which is heat rejection, and constant pressure regeneration. This cycle can ideally achieve the same thermal efficiency as the Carnot cycle, assuming perfect regeneration and reversible process. Though Ericsson's engines were not commercially dominant, his cycle influenced the development of the regenerative heat exchangers and helped shape early thermodynamic theory. The Ericcson cycle is studied today as an idealized cycle, primarily in thermodynamics and engineering education, and is sometimes considered in theoretical discussions of Brighton or Stirling cycle modifications.
The relevance, the application and the relevance of Ericcson cycle. I will not read the definition, I will explain directly. The Ericcson cycle, despite being mainly theoretical, is highly relevant in thermodynamics because it serves as a benchmark of maximum efficiency. It's ideal use of isothermal and isobaric process with heat regeneration make it a theoretical best case scenario. While not directly used in a practical engine, its principle heavily influenced the design of generative systems like the Stirling engine and advanced power plants. Essentially, it's a valuable educational tool. It's helped engineers understand energy efficiency, heat recovery, and the limits of thermodynamic performance, guiding the development of real-world application.
Good morning everyone. So today I will discuss the 1 to 2 isothermal expansion, where heat is absorbed and the gas expands. So the temperature is constant, it's called T1. You can see that in the formula. So also the gas performs work and by pushing a piston or doing mechanical work. This expansion described by the W equals RT IN and V1 over V2. So where the W is work done and N equals number of mole and R is universal gas constant and T is the constant temperature and V2 and V1 is the final and initial volume. So to proceed to process 2 to 3, the isobaric heat rejection. Pressure remains constant, volume decreases as the gas cools, heat is rejected to a regenerator, or a device that temporarily stores heat, and the heat rejected is calculated as Q equals NCP and T1 minus T2, where Q heat rejected and Cp is the specific heat at constant pressure, and T1, T2 is the initial and final temperatures.
Step 3 and 4. Isothermal compression. Isothermal. This means the temperature remains constant during the process. Heat is transferred to maintain a constant temperature. Compression. The volume of the gas decreases, work is done on the gas to compress it. Heat rejected. Because the temperature is held constant while the gas is compressed, heat must be removed from the system to prevent the temperature from rising. This heat transfer is to a surrounding colder environment. Gas. Compress, the gas pressure increase as its volume decreases. Step 4 to 1. Isobaric heat addition. Isobaric. This means that pressure remains constant during the process. Heat addition. Heat is added to the gas, increasing its internal energy. Gas heated. The temperature of the gas increases due to the added heat. Pressure. Constant. The pressure remains constant because the process is isobaric. The volume of the gas increases, accommodating the increased temperature without changing the pressure. So, in summary, these two steps represent a portion of a thermodynamic cycle. Step 3 and 4 involves compressing a gas at a constant temperature, rejecting heat to maintain the temperature. Step 4 to 1 involves heating the gas at constant pressure, causing the gas to expand. That entire cycle would involve additional steps to complete the loop, returning the gas to its initial state. The specific type of cycle depends on the other steps in the cycle.
PV diagram, which are the important tools in thermodynamics to analyze process, involve heat, work, and energy. PV diagram. This diagram shows how the pressure and volume change in a thermodynamic process. Two isolation curve lines. These represent processes that occur at the contained temperature. Two isobaric lines. These represent processes that occur at contained pressure. These diagrams help to visualize work done during a process, as the area under the curve represents the work. TS diagram. This diagram shows how the temperature and entropy change. Two horizontal lines isothermal change that indicate contained temperature process. Two curved lines isobaric. This indicate contains pressure process. This diagram is useful for understanding heat transfer. The area under the curve and TS diagram represent the heat added or removed from the system.
Efficiency of Ericcson cycle. The efficiency of the Ericcson cycle is theoretically equal to that of the Carnot cycle, provided that the heat regeneration is perfect and the working fluid behaves as ideal gas. So the formula of this topic of the efficiency of Ericcson cycle is the thermal efficiency equals 1 minus Tc over Th. So that the N is the thermal efficiency and the Th is the temperature of the hot reservoir or N Kelvin, and the Tc is the temperature of a cold reservoir and N Kelvin.
So here are some sample problem of an efficiency of Ericcson cycle. So problem, an Ericcson cycle operates between a hot reservoir at 1000 Kelvin and a cold reservoir at 400 Kelvin. So the required of this problem is the thermal efficiency of a cycle. So the given is Th as 1000 Kelvin and a high temperature, and the Tc is the 400 Kelvin at a low temperature. So the required is the thermal efficiency. So the formula of this problem is the N equals 1 minus Tc over Th. So the solution is the N equals 1 minus TL over Th. So the solution, N equals 1 minus Tc over Th.
N equals 1 minus 400 Kelvin over 1000 Kelvin. And we need to divide the 400 and the 1200 Kelvin to get N equals 1 minus 0.333. And the final answer is N equals 0.667 or 66.7%.
So today, I'll be discussing about the advantages and disadvantages of Ericcson cycle. The Ericcson cycle offers high theoretical efficiency equal to that of the Carnot cycle due to its use of isothermal process and ideal heat regeneration. It effectively recovers and reuses heat, making it conceptually valuable for understanding advanced thermodynamic principles. However, its practical implementation is limited because achieving perfect isothermal processes and efficient regeneration is technically challenging. It also requires complex and bulky heat exchangers, and the slow heat transfer rates reduce its suitability for high-power applications. As a result, the Ericcson cycle is rarely used in real-world systems despite its theoretical advantages.